Hello, everyone. My name is João, and I am a PhD student at the Brazilian Center for Research in Physics, working under the supervision of Professor Mark Casals. Today, I'm presenting a work we are doing in collaboration with Robert, Eduardo, and Achim, whose title is A First Approach to Entanglement Harvesting in 3+1D Schwarzschild Spacetime. And to begin this talk, it would be good to explain why we're doing that in the first place. So the phenomenon of Hawking radiation is predicted by a semi-classical approach, which is grounded on two well-established and tested theories of physics, general relativity and quantum mechanics. However, such phenomena led to a long-standing discussion, which is the so-called information loss puzzle. The information loss puzzle is interesting on its own. However, it raises two questions that are also interesting. If information is lost, then how is it erased? And if it's not lost, then how does it encode it in the field state at the end of the process? Understanding the correlations in the quantum state of a quantum field that lives on a background space-time containing a black hole might lead to insights about these two questions. Now, when trying to model this situation, things become tricky, especially in the Schwarzschild black hole spacetime. However, we don't need an exotic quantum state nor a complicated quantum field to study correlations. The ground state of a massless, scalar, minimally coupled quantum field already have built-in correlations that are tightly connected to the background spacetime. The broad aim of our research is then to build knowledge about such correlations in the 3+1D Schwarzschild spacetime background. And we begin that by studying how entanglement harvesting works in such a spacetime. Well, a good starting point for that would be to understand what is entanglement harvesting. And for that purpose, I will provide a simple example. Consider three quantum systems, A, B, and C. System A has only 1 degree of freedom, system B has only 1 degree of freedom, and system C has several degrees of freedom. Now, initially, let the quantum system A be in its ground state, the quantum system B be in its ground state, so that the joint quantum state of the system AB is a product state, it is a separable state, and let the system C be in some entangled state. The correlation in between the internal degrees of freedom of system C are depicted here in green. Now, for a time short enough such that systems A and B can't communicate by sending signals through system C, we turn on interaction in between systems A and C and B and C, so that systems A and B are not interacting directly. Then we turn off that interaction. At the end of the process, systems A and B might end up entangled, which is represented by this green line joining them. And this, of course, the state of the correlations of system C will be different from what it was in the beginning. What is important here is that although systems A and B were not directly communicating nor directly interacting, they ended up entangled. And in that case, we say that they harvested entanglement from system C. In general, entanglement harvesting can be understood as a phenomenon where two localized quantum systems get entangled by acquiring entanglement from a background quantum field. Now, in that example, it was very simple to tell that the entanglement was acquired by harvesting. After all, systems A and B were not causally connected. I mean, they were not able to communicate nor interact directly. However, what about the case when systems A and B are causally connected? Are we able to distinguish entanglement acquired by harvesting from that acquired by direct communication? And if so, how can we do it? Well, in that situation, we can resort to the Wightman function of the background quantum field that is in some quantum state. It happens that the entanglement resulting from the imaginary part of the Wightman is not due to harvesting from the background field. That is, if we evaluate some entanglement quantifier and if that quantifier is dominated by the contribution coming from the imaginary part of the Wightman, we can conclude that the resulting entanglement is not being harvested from the background quantum field. In that case, the entanglement is acquired by direct communication. We also have a statement for the case when the entanglement quantifier is dominated by the real part of the Wightman function. And it's as follows. To lead in order, the entanglement resulting from the real part of the Wightman function is not due to direct communication in between the detectors. That is, if we evaluate the entanglement quantifier, and if that quantifier is dominated by the contribution coming from the real part of the Wightman, we can conclude that the resulting entanglement is not coming from direct communication in between the two systems. And now, a lot is already known about entanglement harvesting in the flat spacetime case. Specifically, given a massless, minimally coupled quantum scalar field on an n+1 dimensional flat spacetime background vacuum, entanglement in between a pair of causally connected particle detectors is dominated by direct communication. Now the question is, does such statement carry over to the 3+1 dimensional spacetime? This is the precise question we try to address in this work. Now, to study the possibility of harvesting for causally connected particle detectors in a Schwarzschild spacetime, we use the following setup. We place a massless, minimally coupled quantum field phi on a Schwarzschild spacetime background. Well, the representation of the spacetime is in this diagram on the right. Now, on that spacetime, we place two identical Gaussian switched static Unruh-DeWitt detectors, A and B, which are point-like, and they are positioned at the same radial coordinate with an angular separation gamma. Now, to understand what I mean by Unruh-DeWitt detectors and Gaussian switched, it's useful to take a look at the interaction Hamiltonian, which is given by this expression. So this Hamiltonian governs the interaction in between the particle detectors and the background quantum field. We can see that it is proportional to n, which is the redshift factor, also known as the lapse function, lambda, which is the coupling constant, and eta, that eta is the so-called switching function. The switching function plays the role of modulating the intensity of the interaction as a function of time. And in this work, we are using a Gaussian as a switching function. So this is why I say that the detectors are Gaussian switched. And a plot of the switching functions used is shown here at the bottom right. So we can see that, for instance, let the orange plot be the switching function for detector A. So the interaction in between detector A and the background field is most intense at the coordinate time t equals to 0, and then it decays. So this is the role of the switching function, and this is how it works. Now, Unruh-DeWitt detectors are essentially localized quantum systems that interact linearly with the background field. And the advantage of using this particular model of particle detector is that they are realistic, in the sense that one can realize it in a laboratory. So at least in theory, if we ever manage to get close enough to a non-rotating black hole, we might be able to realize this setup and verify its results, well, in, let's say, real life. So the word line that the detectors follow in this setup is represented by this red dashed line. So this is a line where the r coordinate is equals to a constant, and we can also see the regions where the switching functions are stronger plotted in this space-time diagram. Now I set up my system so that the initial state, that is the state at the coordinate time equals -infinity, is given by this expression, where rho AB is the joint state of the detectors. So we can see that our detectors are set up to be initially unentangled and on their ground state. And also they are not entangled in any sense with the background quantum field. This is initially. Now, after a long time interval, when t, the coordinate time, goes to infinity, we trace out the field degrees of freedom to obtain a density matrix describing the joint state of the particle detectors at the end of the process. And from that density matrix, we can evaluate an entanglement quantifier called negativity. And now that is done to leading order in perturbation theory. Now, in the negativity, which has this expression, we'll see many terms here. Well, what is very important about it is that these L terms are local terms in the sense that LAA depends only on detector A and its properties, and LBB depends only on detector B and its properties, while the term M depends on both detectors, so it is a non-local term. On top of that, both L and M are essentially given by an integral of the Wightman function against some window function that depends on the details of the detectors. So one can think of L and M as essentially being integrals of the Wightman against a window function. This is important to enforce because in order to decide if the negativity is dominated by the real or the imaginary part of the Wightman, what we do is to substitute in the expression for M, the non-local term, the complete Wightman by the real part of the Wightman, then by the imaginary part of the Wightman, and then we compare how the resulting negativity looks when evaluated in these different setups. We repeat the calculation of negativity for the Hartle-Hawking and the Boulware states. The Unruh state is an ongoing work. Now, in short, we fix the peak of A's switching to be equal to 0. So whenever you look at a plot in these slides, you can assume that its switching function is peaking at the coordinate time t equals to 0. This is an arbitrary choice. And then we vary both the peak of the switching of detector B, so we vary this value, so we move the blue Gaussian to the right and to the left, if wanted, and then we vary the angular separation in between the detectors A and B, and we look at the resulting negativity. So the result of that calculation for an angular separation of pi, that is, for antipodally placed detectors, will be shown in a short video. Now notice that despite being a video, it is not representing any sort of time evolution. It is only representing different choices of T0B. That is, different choices of the T coordinate when the switching function of detector B peaks. And in our plots, I will use HH to refer to quantities that were evaluated with the Hartle-Hawking quantum state, and B to refer to quantities that were evaluated with the Boulware quantum state. Now, the video goes like this. And now I'm going to explain what we have just seen. But before doing that explanation, I need to say a word about caustics. So I will show another video where we'll see how the light cone propagates beginning from this blue dot here in a Schwarzschild background. We see that it begins essentially like we know that it does in flat space-time. However, as it approaches the horizon, it starts to hug the horizon. And notice that it will never enter the horizon because we are describing it in coordinate time. At some point, the light cone will self-intersect, as we can see here. The point where the light cone self-intersects is the caustic point. So this is the caustic point. And we see that it just propagates to infinity as the coordinate time passes. Okay, now by looking at the top right plot, what we are seeing here is the following. For this plot, what happened is that the peak of the Gaussian, the peak of the detector B switching happens before the caustic of A's light cone forms. And in that case, we see that there is nowhere where the complete negativity for both quantum states, so where the solid lines are dominated by the real part of omega. So what happens here is that most of the negativity is dominated by the contribution coming from the imaginary part of omega, which is this N minus. N minus is how I'm naming the contribution to the negativity that comes from the imaginary part of omega, independently of the R coordinate we choose. So there is no there can be almost no harvesting. We can't tell if there is harvesting in this setup. The answer is that it's dominated by direct communication. However, if we choose T0B, if we place the peak of detectors B switching function to be large enough so that the caustic has already formed and has already formed, is sufficient, then we might be able to see entanglement. And this is depicted in the middle and in the bottom plots. So what is different here is that if you take a look at for instance, this green line, it was very small in the first case and it dominates in the second case. So what happens here is that, and the green line, it is the line representing the contribution to the negativity that is given by the real part of the Wightman. So what happens here is that, well, most of the entanglement is being produced by the real part of the Wightman. If we choose to place both detectors at, say, r equals 3. So we are possibly taking a look at harvesting for causally connected detectors in that case. So what I mean is that we can't rule out the possibility of harvesting using the Wightman function criteria, as we could for the flat spacetime case. Now, why is this happening? Well, what happens is that as the caustic forms and reaches some radial position r, there is a change in the singularity structure of the Wightman function at that point that makes the negativity dominated by the real part of the Wightman. If we place detectors A and B at that radius and let the time where the switching function of detector B peak be large enough so that the caustic has already reached that radius. Therefore, even though A and B are causally connected, it's not possible to rule out the possibility of entanglement harvesting. And now we head to the conclusions. So our work is, to the best of our knowledge, the first one to study entanglement harvesting in 3+1 Schwarzschild. And there are, however, no results about entanglement harvesting in 1+1 dimension, which can be seen in the references pointed here. And especially the 3+1D setup allow us to study effects that comes from the angular separation in between the detectors. And an important example is this one. The existence of caustics might allow entanglement harvesting to happen even when the detectors are causally connected. As I said, we are currently working on including the Unruh state in this analysis, so we have a more complete figure. And our next task will be studying the case of two freely falling detectors in the 3+1D Schwarzschild spacetime background. We use it here. And that was it. Thanks a lot for your attention.
Thank you very much for your very nice talk. And now we move to the questions, comments. Gerardo?
Thank you for the nice talk. Could you comment briefly these results for the 1+1 case, whether they are positive or not, whether you can harvest entanglement?
Well, the results that we have for the 1+1D case, well, out of the top of my mind, I can tell you that what was particularly investigated in the 1+1D case was that there seems to be a region close to the horizon called the entanglement shadow, where the two detectors can't get entangled. And this is, now I don't remember if this was in the first or in the second paper, but this is the most, I mean, the thing that most have impressed me the most in the 1+1D case. And we'll try to take a look and see if this is the same in the 3+1D case. I mean, our objective is to compare our 3+1D results with the existing 1+1D results for Schwarzschild, and also to try to extend the flat spacetime results to 3+1.
Okay, thank you.
Okay, another questions? Hamed Shalabi, please ask.
Hi, thank you so much for the talk. It was fantastic. I just kind of have like a conceptual question, if you don't mind. So a lot of the difficulty of like quantifying the amount of entanglement harvested in this case, is it genuine from like the field, or is it because of communication, right? So in light of that, do you think that some of the results that you mentioned here could be understood as these are genuine results about like kind of like putting lower bounds on the entanglement, or talking about the entanglement structure of, let's say, these field states around the Schwarzschild black hole? or is that conclusion too strong? And you're just stating that the detector coupling and how and the relationship between the detector coupling and the geometry, or like the interaction between the geometry and the trajectories they put your detectors on, is only the thing that we can talk about, right?
Okay, so it's indeed a very difficult issue to separate genuine harvesting from the entanglement by communication, and we can do it very well if the background spacetime is flat. And the reason is as follows. I mean, the argument that this paper follow to give this conclusion is that suppose that you have some background quantum field, right? And you evaluate the amount of entanglement that results for a setup that's just like this in that background quantum field. Now substitute that background quantum field by a classical field. A classical field has no built-in entanglement. It's just a classical field. What happens is that the amount of entanglement that is produced by the imaginary part of the Wightman is the same in both cases. So it can't be associated to harvesting. So we have this strong negative affirmative. Entanglement that results from the imaginary part of the Wightman don't even care if the field is quantum or not. So any entanglement resulting from that is not due to harvesting. Now, when the real part dominates, which is, it's not exactly the point of this paper, however, it is a result that appears in this paper. So this paper shows that to leading order, the communication capacity is independent of the real part of the Wightman. So if to leading order, the entanglement that results from the real part of the Wightman dominates, say the negativity or any other entanglement quantifier of your choice, then what you can tell is that the entanglement is not being produced by direct communication. In the flat space-time case, you could say, well, okay, then we have genuine harvesting here because, well, if I change the background quantum state, I will change the outcome of the entanglement. In curved spacetime, in a curved spacetime, it gets more complicated because in curved spacetime, we know that there is a very specific singularity structure that is common to all Hadamard quantum states. And what I mean by that is that even the real part of the Wightman every Hadamard state shares a common singularity in the real part of the Wightman. So we can't really say that such singularity is a state independent because all Hadamard states share such singularity. However, in the real part of the Wightman, there is also a free parameter that, well, this one is what makes two quantum states different. However, it's very difficult to tell if the entanglement that we see coming from the real part of the Wightman is dominated by the singularity, which is a geometrical property, or by the actual intrinsic definition of the quantum state. So we can't really, it's difficult to settle down to decide if we call the entanglement produced by the geometrical singularity harvesting or not. So I would not go with a very strong affirmation here.
Right, thank you. And just as a quick follow-up then, so could I, for the particular case of Schwarzschild, would the part of the difficulty here be that, like, on this complicated geometry, any signaling through the field would not just be along the light cone, right? So you're going to have the violation of the Strong-Huygens principle, and you would expect signals from detector A and B to kind of propagate along time-like trajectories, right? So effectively, in that case, what you're saying is it's very difficult to separate these from genuine entanglement.
Well, that we can separate that because that would be an entanglement produced by what you posed would be produced by communication. I mean, one detector is able to communicate with the other one by sending messages through the background field. And we can separate that for sure. However, what we can't really do is separate what is intrinsically geometric from what is intrinsically a property of the quantum state. This is what is very difficult to do. So this is why I don't say that we do have harvesting in this case. I mean, I'm not comfortable with such a strong affirmation.
Thank you so much. Thank you so much.
Okay, I think it's time to stop here. Thanks again for this talk.